All right, so I'm going to be talking about section 5.3, which is on surface Green's functions. So the book starts off by just stating that the surface charge that would be induced by some Green's function, at some position r, I guess, is going to be equal to plus 1 over 4 pi times the normal vector, or the normal unit vector, dotted with the gradient of the Green's function. Okay, but it doesn't really talk about where this comes from. So let's talk about that. So let's say we had some volume, and then we had like a conductor inside this volume, okay? So if we had this volume that we're integrating over, which is bounded by these dotted lines, is actually going to be considered the like inside of the volume. And then inside this conductor is actually considered, I guess, outside. Okay, and this wording here is important because if you remember from electrostatics, we can say that the electric field outside minus the electric field inside, dotted with the normal vector, is going to be equal to, and I'm just going to call this n hat prime since that's what we're calling it up here. I guess you could call these prime as well if you want, but it's not super important. This is equal to 4 pi sigma, or sigma over epsilon naught, but in Gaussian units, it's going to be 4 pi sigma. So this E outside, if this is like conductor, like one, the electric field's constant, but also this E, we're going to be deriving it from a Green's function, and the Green's function is only going to be defined inside this volume that we're integrating over, and so we don't really care what's inside of here. So this E out goes to 0, and we're just left with negative E in prime dotted with our normal vector is equal to 4 pi sigma. But you might remember that the electric field is the negative gradient of the potential. Okay? Which means that, or implies that, in this case, the one thing you need to remember is that the Green's function is actually just a potential defined under specific conditions. And so this is actually the negative gradient of the Green's function is equal to E in prime. Okay, so what we have here, when we take this and we plug it in here, is that the gradient of the Green's function dotted with the normal vector is equal to 4 pi sigma, which implies that our Green's function sigma is going to be equal to plus, or sorry, not plus or minus, plus 1 over 4 pi times this n prime normal unit vector dotted with the gradient of our Green's function. Okay, so that's where that comes from. Okay, and then, so how the book words this is that the normal derivative of the Green's function is related to the surface charge it would induce by this whole equation. Okay, and the one important thing to remember was that we got this positive because our normal vector is actually going to be pointing into this surface here, okay? Because it's going to point away from the inside, and it's going to point towards the outside, okay? And so then what we can say from this is that if we think back to our equation for phi based on our Green's function, we knew that it was equal to this volume integral of g rho d tau minus 1 over 4 pi times this surface integral of dA prime, the dA prime vector, I guess the dA prime vector, dotted with the gradient of the Green's function, times, or sorry, the gradient of the Green's function, I guess, times phi at r prime, right? And so, but we just wrote that this 1 over 4 pi times the normal vector dotted with the gradient of the Green's function, which, and if you remember that dA prime is really dA times n hat prime, then we can say that this equation is actually equal to our volume integral of g rho d tau minus the surface integral of dA prime times our sigma of r times our phi of r prime. Okay, and so that means that if we can find the sigma, we can plug into this and calculate phi. So we haven't really done anything unique here yet, except this sigma is not a Green's function, but we can relate it back to chapter 3, where it did talk about something called the surface Green's function, where back in chapter 3 it wrote that we could have like phi of r is equal to some integral over some surface, I think ds prime, times a surface Green's function times phi. And so if we compare these two, oh, whoops, I'm missing. Yeah. So if we compare these two, we can see that negative the sigma term is equal to g, since this is this term is positive. Okay, so what that means is that we can rewrite our phi, or not rewrite our phi, we can write our surface Green's function from chapter 3 as being equal to negative sigma gf. And then my understanding about the surface Green's function is that we want to use it when we have homogeneous boundary conditions on every surface but one. So I guess if you had like I think the example they gave was like a cube. I can't really draw cubes very well, but let's just pretend that this is a good cube. Okay, that's not a great one. Let's just pretend that this is like a good cube. If you had some potential here, I guess v of x, y, and then you just had 0 on every other surface, then and then the other two surfaces were 0, then you could use the surface Green's function to solve for the potential, like inside of this cube, let's say. And so that's really going to be it on the surface Green's function. But once we do some examples later, I think it'll make more sense, because I do think it's quite confusing at the moment.